Okay, so let me start the session number 9. We have 4 contributions, all related in some way to machine learning. 3 of these contributions are by myself and the colleagues from Ostrava, and 1 contribution is from our Spanish colleagues. So I will start with myself. And my talk is more like a application report to about the few-shot learning and industrial data. Would it be possible to turn off the light so it's better visible? So the motivation is not uncommon for the industrial processes to produce a lot of data, and quite often these data are not labeled. So it's just a pile of something. And obviously there isn't really a push to spend the man hour to sift through these data. So I have selected, just for illustration, the data set of the screws. In our contribution, the data sets are unfortunately covered by NDA, so I cannot show them, but I think this is quite illustrative on its own. So if you don't want to spend money and man hour to sift through the data and possibly label them, do we have some other options? And what we can do is we can leverage the foundation models. So recent big models that are quite versatile, often the transformers. And what really sets them apart is that after spending a lot of time and resources on training, these models can be very easily adapted for different tasks. Or perhaps those different tasks are already part of the pre-training itself. So this is the case, for example, for Dino version 3 that was quite recently released. And this model is capable of doing classification, object detection, segmentation, depth estimation, and video tracking. So single model, single backbone is able to do all of this just by changing the output, some output adapter. And that means that whatever this model is producing in terms of embeddings or some sort of feature vector must be quite semantically rich. There must be a lot of information, so we can do all this kind of different stuff using this single vector representation of the original data. And so now the question is, can we use these foundation models on the industrial data using, for example, few-shot learning for classification problem? Now, one thought that we can eventually come to is, okay, so industrial data are probably quite niche, and when these big models are being pre-trained, we can ask how much of that data being pre-trained were related or similar to a industrial data. So in the case, for example, of Dino version 3, Dino version 3 is pre-trained on 1.7 billion images that are curated and taken from 17 billion of Instagram posts. We can make assumption that people don't share on Instagram industrial data, most likely. So then the question is, how descriptive are these foundation model embeddings regarding industrial data, and are they good enough to be utilized for the few-shot learning? And we can also ask, okay, what makes the industrial data different from the pictures you take with your phone? And I would say that, first of all, there are some sort of stable conditions. So quite often we will have camera that is static, doesn't move. Hopefully we also have a good lighting conditions. So those images will be looking quite similar. Second thing, in the case of, let's say, for example, the spectroscopy, trying to find defects or flaws in any kind of products, these flaws might be quite subtle, quite small. It's not exactly visible, but here is a dent. Then here on the neck is a dent. And then there are some like leftovers from the manufacturing process. In the case of the defectoscopy, there is also issue with extreme imbalance in data. So you can imagine that most of the products are coming from the assembly line or somewhere, and they are okay, and few of them will be flawed. So in the terms of machine learning, huge imbalance in data. And then there is, of course, the concern of data privacy. So sometimes we might be not even able to get our hands on the data themselves. They might be encrypted. So also one thing to consider. So in our experiments, we have used 3 different foundation models and 1 convolution network since we're working with images. The convolution networks is Convenext version 2, which I would consider last very well performing convolution network before the transformer came. Then we have a perception encoder, which is vision transformer trained in tandem with language using CLIP. So it's a multimodal trained model. From the paper that shown that for different tasks, you might want to get embeddings or feature vectors from different stages of the vision transformers, for example, from the middle or the end, depending what you are doing. And then the Dino, which is supposed to have very robust embeddings to the point where you can train it on something and then put it on very different data set and just do the K in nearest neighborhood, and you will get really competitive classification results. So regarding featured learning, just to illustrate what is the problem like. So in featured learning, we have a few images per class, and then we do something and try to get the classification of the new coming samples. So in this case, the new coming sample that has been not seen before is called query. And the samples that we have labels for are called support sets. And it's usually written in this way, like 2-way 4 shots. It means 2 classes and 4 samples per class. And so eventually we will get somewhere to this embedding space where we use the foundation model to get the embeddings for every sample. And then with these embeddings, we do something, and that is the subject of the different few-shot learning algorithms. As I mentioned, for example, we could try the very simple clustering or KNN for the classification. So in our contribution, we have tried 4 different few-shot learning algorithms. The first one is called prototypical network, which takes the embeddings of all the samples in each class and just compute the average. So this is average embedding, also called prototypical embedding. And then you just compare the distance of your query image, which is given by the embedding, and whatever is closer, that is the class you assign. The second algorithm is called NCA, which is quite similar, but works slightly different. So in this case, we do not compute the average, the prototypical embedding. Instead, we look at the distance of the query to all of the samples from the support. And these distances we convert to probability. So the closer the query is to a certain support sample, the higher is the probability. And then we sum over and whatever summation is higher, we say that is the class of the query image. Now, this has an advantage. Well, it has an advantage that the outlier is not the issue. So if there is one or two images of the wrong class close to the query, should not have the effect on the outcome. Second, since we are converting distance to the probability, we can use all the tools from our machine learning toolkit to work with it as with probability. So using cross entropy, loss function, and so on and so on. The third one is category of metric learning. So at this point, we don't have this fixed distance anymore. On the previous, we were using Euclidean distance and just converting it to probability. In the case of relation network, what we do is we take the query, join it together with the samples from the support one by one. So is query with each of the support. And we run it through relation network that gives us the score and says how similar is the query to that particular sample of the support. So we get, if we have 40 support images, then we will have 40 scores, which we interpret as a similarity between them. And therefore, we can then use this score to either find the highest matching score or average over it. We can do whatever we want with those scores, with the vector of scores. And the last one is not really a feature learning technique. It's just a simple classifier put on top of the embedding prototypical network, embedding of the foundation model, which you would guess should not really work all that well, because trying to train classifier on 10, 20, 30, 40 images, that's probably not going to work all that well. But to be for the completeness, we have added this as well. So we just take the embedding, run it through single linear layer. With the sigmoid activation, we get something between 0 and 1. Because we are concerned with the binary classification, I should have mentioned, it's either the product it has an issue, a flaw, or it does not. So binary classification. And lastly, I'd like to mention technicalities. And that's, first of all, adapter. So the foundation models that we are using to compute embeddings, they do not train, obviously, because they are huge. We cannot train anything with 40 images. So, but we still want to somehow take the embeddings and try to fit them to our problem domain without overfitting. So what we do is we just squeeze the embedding through some single linear layer that decrease the dimensionality. So for example, from 400 element vector, we squeeze it to 200, 100 to avoid the problem of the overfitting and just to be able to adapt those embedding vectors to our domain. And the second, in our experiments, just for the completeness, we have run the hyperparameter search to find somehow the optimal size of the adapter, learning rates, and these things. And so we have a following table of the results. So we have the 4 embedders, which is the convolution networks, the Dino, and the perception encoder combined with all 4 classifiers. And from the results, we have found out that in this particular scenario, over the 3 data sets, the best performing embedder is Dino version 2, and the best few-shot learning classifier is the relation networks, which intuitively makes sense since it learns the metric itself, the similarity between the samples. So it has the highest, so to speak, degree of freedom. We have also we have also used one more metric because accuracy wasn't descriptive enough for us because we are averaging over 3 data sets. So some combination might perform really well on 2 data sets and fail miserably on the third one, and the average doesn't really capture this. So we also use normalized gap, which is basically the distance, normalized distance of particular combination from the best performing one. So the smaller is the number, the better is the position on the ladder of accuracies of that combination. So if there would be a combination that is absolutely the best, in every single scenario in all 3 data sets, the normalized gap would be 0 for that combination. So you can see that in this case, it's Dino prototypical networks, this one. However, this was done only on the basic data set of the, what is the time? 15? Okay. On the 40 images that we selected for the training. However, there is a second case, apart from just using these images, where we where we extended the data set because you have 40 images and you want to get as much as you can get from it. So we have created augmented data set, which is done by using deterministic augmentations for each sample. So we take one image, make 9 copies of it, make it brighter, make it darker, zoom in, zoom out, and such. And these things are deterministic. It's not your usual training augmentations that are random. And so that means that we have expanded data set 9 times. So from 40, we got to 400, which led to improvement across the board, except for this, I would say, outlier. And which bring us to the final ranking, where the best performing combination appears to be Dino with NCCA, or in general, Dino appears to be working really well. So given these results, what are the insights? What we found out to be interesting or seems to be issues? So first of all, the intra-class variability. There is a low chance that by picking few images or getting few images from some assembly line, that these images will have all the problems captured in them. As I said, there are 4 different kind of defects on these screws, and it is quite unlikely that if somebody gives you 40 images from the assembly line, that all the possible flaws will be there. Of course, I know this because I had the whole data set available to me, so I could look. But if I don't have the whole data set and somebody just tells me, we want to buy something from you, some algorithm, here is 40 images, do it. You will not have the whole information. So that seems to be a challenge, especially if you are tuning your adapter for the squeezing the embeddings. You'll be training on the, so to speak, incomplete data. The second thing we thought might be interesting is to use LoRa, a low-rank adaptation, to just fine-tune slightly the embedder, which didn't work. So that was another result. And since my time is running out, I think this is the last slide. Thank you very much. Questions? Okay. Well, I am chair myself, and very obvious to me, all of it. So I will not ask myself any question, and we can go to the second talk. Okay, of course, please.
Confidence score on how confident
Yes, it would depend on the classifier, this few-shot learning algorithm. The one that works with probabilities, you can interpret the probability as sort of confidence, or you could introduce it as a new argument that is being trained. I think in case of distances, I don't know if you could consider distance to be confidence. Like further it is, the lower confidence score you have. So thank you very much. Can we get the second speaker now? is the microphone.
Hello, is it working? Yeah. Okay, so yeah, my name is Javier. I'm from Pamplona, and I'm a brand new PhD student. So this presentation will be slightly different to most of the presentations you will see in the Congress, because I won't present any theoretical or practical results. But in contrast, what I will do is introduce the concept of uncertainty quantification, and I will review the methods that best work in the case study of electroencephalogram data. So first, where does this come from? Well, we've all seen very powerful models that perform very well in some task. For example, taking a picture of a cow or a horse and predicting whether it's a cow or a horse. And when we happen to give the model another animal that not a cow or horse, even though it's well trained, it will predict one of those with really, really high confidence, which is a problem because it's a fake confidence. And this is summed up with the fact that most of some models operate often like a black box, and it's very difficult to track where the prediction comes from. So that there, the uncertainty quantification field comes to our mind, because we need models that know what they don't know. So we need a way of measuring the uncertainty of a model when predicts something. But even just measuring how confident a model is not always enough, because let's make let's make two situations. Imagine we have a machine learning model that reads EEG data and tries to predict whether a patient is going to have a stroke in the next 30 minutes. And it's very confident and gives us a prediction of a 50% chance that the patient is going to have a stroke. And then we have another situation where the model reads some EEG data, but this data is really weird and doesn't know what he's seeing, is very noisy and has no clue what to predict. It will predict as well 50% chance that the patient will have a stroke. But these situations are very different and should be treated very differently. So we should distinguish which between types of uncertainty. In the first case, it is just pure randomness of the world. But in the second situation, it's just that the model is ignorant about what is happening, because then the signal is very noisy. So here, that's why in the uncertainty quantification field, they distinguish between two types of uncertainty. The aleatoric uncertainty, which is in principle irreducible, that is just inherent to the randomness of the world that we live in, whereas the epistemic uncertainty is related to the ignorance of the model, or just that the model hasn't been trained with that data that is trying to predict. And this is in principle reducible, but just by improving the model or adding more data to the training data set. So how is uncertainty quantified in the literature? There exist several models to do this, and these can be segregated in these two different axes, depending on if they are frequentist statistic based or Bayesian based, and whether they predict just a single point or they predict a set of possible classes that try to guarantee that the true label is in that class. So why EEG data? Why have I've chosen EEG? Well, electroencephalogram is a special, well, it's neurology, and in medicine is a field where we need to have a special care when we make predictions, especially when we make wrong predictions with high confidence. So having a measure of the uncertainty that the model has when it makes a prediction is crucial in medicine. On top of this, electroencephalogram, if you're not familiar with it, it is measured with some electrodes in the scalp that measure the change in the magnetic field, and in that way you can measure the brain activity. But these signals are very, very noisy, and they are very susceptible to changes in the temperature, in other factors. So it is high aleatoric uncertain. So in that sense, we can test that our model measures that in a correct way. As well, we have high epistemic uncertainty because every subject, the activity of every subject is very different, and even within subjects, from one experiment to another, can change a lot. So in this way, we have also a way of measuring the epistemic uncertainty. So what's the gold standard in EEG classification with uncertainty quantification? Well, it is complex to just get a gold standard, but the field balances between these three objectives: statistic rigor, computational efficiency, because sometimes we have to make decisions in seconds or in real time, and also clinical utility. However, some consensus are coming up, and for the gold standard in the best predictive accuracy, the best calibration error, and out of the distribution direction, the deep ensembles are the best, at least for the moment, or for most of the cases. And for those that are not familiar with deep ensembles, it's just an architecture that is trained m times, and then you have m predictions, and in this way you can measure the aleatoric uncertainty by the uncertainty of each model and the epistemic uncertainty by the consensus of the models. However, sometimes the safety is crucial, and then we could come with another safety gold standard, that is conformal prediction. I won't get into detail of this because it's quite complex, but the main idea is that instead of having just a single point prediction, we have a set of predicted classes that guarantees a marginal coverage of X%. In most of the cases, it's 95%. And for example, in this case, imagine we have a model that predicts, these are the probability predictions of the model. It won't make any sense to just say that the predicted class is A, because the difference between class A, B, and C is not very big. It would make more sense to just predict a set of possible classes, or that the classes that guarantee that the chance that the true label is going to be in the predicted classes above a certain threshold. So yeah, there are, despite that some improvements are being made in the uncertainty quantification field, there are some challenges and limitations that are inherent to EEG data. For instance, most of the methods that try to measure uncertainty, they assume that the data are that the data is stationary. This means that every point is extracted, or every sample is extracted from the same distribution, which is not the case in EEG data. Because noise can change from time to time. The electrodes can change the signal field, and it's very non-stationary. So that's a challenge. Also, we have in the field of medicine the ground truth problem, because sometimes it is not just that the class is or the sample is uncertain, but also sometimes the label is uncertain, because some experts could not agree in the label or not agree in what they are seeing. So, and this is not captured in traditional cases. And also, there is a clear trade-off between accuracy and latency. For example, I've mentioned that the best for the accuracy in this case should is often the deep ensembles, but for that you have to train deep neural networks, and then you have to predict with all of them, and this is not feasible when you need very quick predictions. So for those cases, you should use another model that is faster and that is not that computational expensive. So these are main takeaways for the presentation. First, standard deep learning models can be overconfident even when they are making terrible predictions. Then uncertainty quantification is key for building trustworthy AI, especially in fields like medicine. And also the distinction between aleatoric and epistemic uncertainty is important, as I mentioned with the example in the beginning. And also that EEG analysis is challenging and relevant applications. It's a challenging and relevant application domain for uncertainty quantification. So yeah, thank you for your time.
It's difficult to ask. The presentation is general. However, when you see this great variety of data, yeah, so in order to produce some reasonable consequence, yeah, the first recommendation is to reduce your data. Yeah, in your case, yeah, probably to regularize, yeah, your data, because really it is affected by significant noise. Noise also can be somehow model, yeah, if you know how to do it, yeah, or things like that. And then, yeah, as you said, yeah, so the labeling is according to some experts, and they can be in a conflict. This means that you can select experts, yeah, that who agree on, I don't know, so this or that, and then create model according to these experts. Yeah, this is quite normal in medicine and in biology as well. Yeah. So there are some approaches, yeah, how to overcome these difficulties, I think. Yeah. And if you can really include this type or other type of recommendations in your model, probably you will obtain more supportive results.
Yeah, that's a good point. Yeah, but sometimes it's difficult to try to cover it all. Yeah, but we are trying to make the best of the model. So even when we have uncertain labels from different experts, I think that also gives us information about the label is itself and the sample itself that is uncertain. I think the world where we live is uncertain in some ways, so we are not sure about the decisions we make. So just having a measure or having a way of capturing these, I think it could be also interesting, apart from trying to try to couple for the noise of the EEG data or anything else. Yes. Thank you.
Imagine the data are sequential, so you treat it as a sequence, sequential data. Are there any other like unique properties that comes from the fact that it's medical data?
Not that the fact is medical data, but just that comes from electroencephalogram that is very noisy and non-stationary, but not that the fact is medical.
I switch around the electrodes and such, I will get different values, maybe different intervals and such. Do you know how widely does it differ? Like, is it really that big of a difference? Like, for example, from patient to patient, if I keep the device and I switch between the patients, do we get like different?
Yes. And even with the same patient and in the same experiment, this can change from time to time. Yeah, it is just because it is a very difficult way of measuring brain activity. And yeah, the patient could be tired, the electrodes could be misplaced in some way. Well, when you do these experiments, you try to, as Irina said, you try to select the best samples that you have. So for that, you make several experiments. And in some cases, when you get some strange artifacts, maybe you have to decide whether you keep them or you have to just not use them because they are not useful. So if at some point just the electrodes switch and they are not useful anymore, then yeah, but there is, even when they are useful, it changes between time to time, so it's difficult.
Does anyone else? Okay.
Yes, of course.
So I'm wondering, you mentioned the accuracy versus latency. How often is it the case that you need to do it online?
Yes.
Classification, is it like common case?
For example, there is a special case of application for EEG data of brain-computer interface, where it is used for post-stroke patient, like a patient that have suffered a stroke and they are trying to recover how to move their hands, for example. So these devices often help them to predict whether they are trying to move the hand or not, and this helps them, yeah, to train in a more efficient. Yes, that's it. Like, yeah, it's a way of saying, okay, yes, you are trying to move the right hand. Yeah, keep doing that so you recover faster. And this needs to be in real time. Yeah. So in that case, maybe you don't need the best accurate model, but you need one that's, yes, that's it.
Any different classifier that you try to get the spread of these individual candidates?
Yes, that's a very good point. That's exactly like what deep ensembles try to do, how they measure epistemic uncertainty, like the model ignorance. When we have several models and you assemble them and they disagree, this means that the model itself is uncertain about the label. So that's a way of measuring the uncertainty, epistemic uncertainty. Yes. And you can do it also not just with deep learning models, you can do it with several different architectures and see if I'm doing an ensemble of them. Yes, of course. Yes. Yes. Mm. Yeah. Yeah, simulated ones. Thank you.
Hello, everybody. My name is Emro Gala. I'm from the University of Ostrava, and I would like to present our work on using. I would like to present our work on using graph neural networks to predict subgoals in a logic game called Ricochet Robots. Okay. I will cover our motivation, the problem, our approach, experiments, and results. Okay, so our broader goal is to design agents that can explore complex state spaces by predicting some interesting or useful subgoals. This can be important for NP-complete problems, where basically exhaustive search through that space is not really possible. So this work is, I'd say, mostly sanity check to make sure that graph neural networks can actually learn, making sure if they can actually learn how to predict subgoals based on some manually designed heuristic. So the game is NP complete, but it's simple enough where we can make many training data for it. Yeah, and on the right, you can see just a simplified example of the game board where the goal of the red robot is to get to the red target square. So let me explain the game mechanics. So Ricochet Robots is a game played on a square grid where you have multiple robots of different colors. There are walls that can block movement. What's important to say is that the robots, the red circles, can only move either horizontally or vertically. The key constraint is that once a robot starts moving, it can only stop once it hits another robot or a wall. So the goal is to get a robot of a matching color to the target tile. Simple enough. And there can arise a situation when the robot cannot get to the target by itself, like here, for example. And you need another robot to act as a stopper. So like here, this move wouldn't be really possible. Like I said, it would collide with the rules. So you would somehow need to get another robot here so it can like stop here and then continue to the target. Yeah, and the game is, like I said, NP complete with K robots, which makes this reachability complex. Yeah, non-trivial. So we represent each game state as a directed weighted graph. Basically, where every node is the tile and every edge is feasible robot movement in the game board. We assign weights to each edge based on whether the move is dependent on other robots. In that case, we assign it 10. And if the move is independent of other robots, we assign it a weight of 1. Okay, so our heuristic to basically find some interesting subgoal is based on these three concepts. First, we look in the game board for tiles. We call them final components that basically the robot, once it is in one of these tiles, it can reach the target tile without any help. Then we have transition tiles. These are tiles directly adjacent to the final components. And basically, there you need help from another robot to act as a stopper for the target robot. And we score each of these final components by summing up the cost to get to the target from the final component and cost of path from the initial configuration of the target robot to one of the final components plus the helper robot. It's both of them. And yeah, this is the heuristic that we're basically trying to teach the neural network. Here is an actual example of the game board that we use, on which the model actually trains. It is a 16 by 16 square grid. Yeah, the individual circles are the robots. You can see the target tile here. Here, it's about getting the red robot to the red target. And these orange squares are the final components. Yeah, you can see that from any of these, you can get to the target without any help of other robots. Just a simple example how to solve this one configuration. If you didn't maybe already solve it yourself, but here first you would take this green robot, you would move it up, it would stop by the wall here, move it left, leave it on this tile. Then you can take the red robot, move it up, and it would stop by this green robot, and then you can move it to the target tile. That's how you would solve this configuration. And yeah, these are just the transitional tiles. Yeah, so as you could see, you move it to this one, and from here you can get to the final component. Okay, so we thought of two tasks to classify for our model. The first one is to just simply classify which tile belongs to the final component. And the second task is to classify which one of these final components is actually the best subgoal, which one has the lowest score. Just a quick just to say how it works in principle. So we first of all we make 15,000 different configurations of this game, and the model that we use actually is recurrent graph attention network, just to be precise. And so each node has 4 features assigned to it. So vector. For nodes, it's just signaling whether in the tile, if it's empty, if there is a helper robot, a target robot, or if it's the goal, the target tile. And we also assign these features to edge, but they tell us whether the edge is dependent or not, and the direction of the edge. And this is the input for the model. Yeah, then you project these 4-dimensional features, vectors, into a higher dimensional space. Yeah, so for us, it worked the best amount of dimensions that work for us, 4 dimensions. So 64 elements in the vector. And it's now some kind of representation. It's not just some features. key point is that there is a message passing between the nodes. So what you do is for every node, you combine information from their immediate neighbors, and you do this 7 times. Again, this is like a parameter that we found out was the best for us. So the information spreads across the entire graph. Yeah, first you have just the information, for example, for the node A. First you have information just from the node B and C, but on the second iteration, these nodes already have information from D, T, and A, and N. So basically, at the end, each node has some kind of knowledge about the whole graph. And so we get some kind of rich representation for every node. And yeah, so this is like after the 7 rounds. And finally, we can make our predictions. So just going from the high dimensional space to just like 2-dimensional to classify the classes for our task. Yeah. So here are our results. You can see that okay, so we first do metrics based on individual nodes, and then on graph based metrics. For the node level metrics, we can see that the first task, which is to just classify if the tile belongs to the final component, has very high accuracy. Overall, even for the graph level metrics, we get almost perfect results. The second task is a different story. We get pretty good accuracy, but when we look at other metrics, it starts to get not that pretty. And what's important for us is the graph level metrics, where you can see that we get around 66% correctly labeled graphs. Okay, so what did we demonstrate? So like I said, the part of this work was just to sanity check whether graph neural networks can learn to predict subgoals from manually designed heuristics. So yeah, that did work. The first task is quite easy. It was really easy for the model to predict. The second task, not so much. We only got 68%. And you might ask why the difference. So the first task is basically a simple graph traversal with some local information. It's not difficult at all for the model to learn. But the second task is, in a way, a global optimization. The model needs to reason about multiple robots and compare different paths across the entire graph. So it's much more difficult. But it shows us that there is some potential that it can actually learn something. Like it still got right like 2/3 of all cases. So yeah, there is still we can see that there is some potential in it. Okay, so we want to add also regression to the model, not only classification. Mainly, we want to compare the graph neural networks with sequence models like transformers. And yeah, our final goal, I'd say, is that we can design agents that can autonomously discover some hierarchical structure in complex planning domains. Thank you. Oh,
All of them. Ready? Last slide. But
Thank you. So you were talking about the helpers and the robots. Is the role of the helper predefined, or that
Yeah.
any robot can be helper?
Like I said, one of these robots is a target robot. It's
So it's
matching-
predefined. That one,
Yeah, it's predefined.
so the red one needs to get there. For
Yeah, the red
example, in
one
this
needs
case.
together, and the other robots need to help the target robot.
Right. And the helpers, they do move the same way the
Yeah,
robot
yeah,
does.
yeah.
So
They have the same rules.
okay, so they just have a different role, but they move and everything is the same.
Yeah.
Okay.
They just have a different goal.
Right. Then my second question is regarding this projection to higher dimensions of the vector from 4 to 64.
Yeah.
Why? What's the
That's
reason?
That's like a hyperparameter tuning. Just
I know, but what's the purpose of going up? Why not stay at 4?
yeah. So it's just like what the model does. It's like some kind of you want to build up a rich representation of the entire graph, like so each node like has.
So the node goes from 4, but
Yeah,
the
like
project.
from 4 of these original features to 64 some features. We don't know. It's just like some.
And then this message passing is
Yeah.
changing this vector of 64 values.
Yeah, you basically it's like to learn the ways.
Right, so it's some kind of maybe like a memory or something that you can
Yeah,
write into.
you can. I guess.
Information from the others coming and you just change it
Yeah.
accordingly.
Yeah.
And so eventually it somehow relaxes the whole thing and
Yeah, it will
converges to
come.
some
It will come to some kind of relaxed state where nothing changes anymore.
Right.
That much.
So that's like your stopping condition. It stopped changing. That's about it.
Yeah, so that's where the 7 iterations basically came from.
Right. Now, so if I understand correctly, like the main goal is to move from somewhere to somewhere, and then the sub goal is this classification or evaluating the tiles.
Yeah, so the sub goal is like the lowest. Like I said, we score each of these final components,
Right.
and one of them has like the lowest score. Just like it takes like the goal is to get there in a minimum amount of moves. Maybe I didn't mention that. Yeah, you want to get like.
So that's the main goal, and then the sub goals is the task 1, task 2.
The sub goal, no, that's actually the second task to find the like best sub goal, and best sub goal is the lowest scored final component.
Okay. And okay, so my last question is, you mentioned that the task 2 is a bit harder and didn't get as high accuracy and the other metrics. Does it mean you didn't get it there in the same amount of time you gave to the task 1? What I'm trying to ask is, if you would train longer, if you would change something, do you think in principle would it be possible to also achieve the very high accuracy similar to task 1?
Okay, I'm not sure about the specifics, but I believe that like the model just didn't learn any further. It just like stagnated.
So it's inherently hard, and
Yeah,
that particular model peaked, and that's it.
Yeah, you would need to like make the model more complex, or maybe give it more training data, stuff like that, I guess.
And since you got synthetic data, you can do that. You could, if you wanted to.
Yeah. You could.
And how many you mentioned it? 50,000.
15,000 different configurations.
And this sample generating program, does it take a long time to generate the synthetic data?
Okay, actually, I haven't generated myself. I
It's just
don't know how long it took to
Out
generate.
of curiosity, if you
I
could just
say a few hours.
few hours, so it's not like this with some time. Okay.
It definitely takes some time because you still like you need to, compute all like these paths and assign all these like.
So there is actually some that computes
Yeah.
paths. So
Yeah, you in order to get the goals, like what the model is actually supposed to learn, you first need like to compute it yourself.
and is it some particular algorithm for finding like shortest path or the best path? Because this is optimization problem on its own.
Yeah, but you have the additional rule of these robots that they can only move horizontally, vertically, but they stop like when they hit a wall or another robot. It's not just simply like, okay, I can go like this, and this.
Yeah, I just
Yeah.
meant that the generating data itself and these labels or
Yeah.
these paths must be also quite interesting.
Uh,
If somebody had to code it, how do you do it? Anyway, that is maybe for the later discussion. So thank you one more time. The fourth speaker is David Adamczyk.
So thank you for the introduction. Hello, everyone. My name is David Adamczyk, and I am from University of Ostrava. And in this presentation, I am going to talk about how we can train large language models to yeah. In this presentation, I would like to talk about how we can train large language models to imitate CDCL solvers. So I would like to start with our motivation. So our research question is, can we train large language models to execute an algorithm step by step? So we don't want to memorize only the input and output pairs, but we want to predict next token, and we would like to see if it is possible. So for this problem, we choose SAT, and we choose SAT because it is well-defined problem, and we can very easily check or verify if it is correct. So I would like to mention we don't want to replace CDCL solver by large language models. We would like to test if large language models can learn algorithmic reasoning. So this is our the formula and the output, but we would like to predict all of the tokens from the execution trace. So we can see if the model can follow the algorithm step by step. So for people who are not familiar with the SAT, I would like to say how it works. So we have the formula in conjunctive normal form, and we would like to ask if we can assign true or false to make this formula true. So the output from this algorithm is SAT for this case, or unsat. And SAT is NP-complete problem, and it is the fundamental problem from computer science. The naive approach, how we can solve the SAT, is just brute force the other combination, but it is not good idea because there is the problem with exponential growth. So for example, for 10 variables, it is over 10, it is over 1,000 of combination, and for the 20 variables, it is over 1 million of 1 million combination, and so on. So we would like to find some smarter algorithm how to solve the SAT. So one of the possible solver is CDCL solver. It means it is conflict-driven closed learning, and it works in this way. So we have basically the main loop, and in the main loop, we just pick a variable, assign true or false, and then we can propagate I mean, the deduce first values in the formula, and we can detect the conflict. If there is no conflict, the loop just iterates and it is all. And if the algorithm finds the conflict, we can analyze the conflict. We can learn a new clause to prevent repeat this error, and we backtrack the assignment to the previous step. So here is the simple example. We have this formula in conjunctive normal form. There is the clauses, and the first step is the decision. Just choose the unassigned variable, and we assign, for example, the true at the first level. The next step is basically the unit propagation. So we check clauses to force assignment, and we can propagate. So in this case, the unit propagation deduce X3 without guessing. It is the logical inference. The next step, we just want to assign variable to X2. So we are going to the level true, and we assign X2 is true. So we check the clauses, and we find in this clause we have the conflict. So there is the conflict, and we can start with the conflict analysis, and we are going to the next step. So the algorithm will find why did conflict happen. So we can find the right assignment, and the algorithm can learn a new clause. So the key insight from this conflict analysis is the algorithm can learn, prevents these exact mistakes. So the same mistakes can't happen again in the next steps. So we can finish this with backtrack and the solution, and we find our assignment for this formula. So this formula is satisfiable. So this is all for the SAT CDCL solver. And I would like to continue with our architecture, how we can connect the large language models and the interactive sketchpad. The interactive sketchpad is basically from DeepMind and MIT, and it is a special store where the language model can store some information during the inference time. So basically, you can imagine this as a CPU, because it can perform some steps like decide, propagate, and so on. It can store some information to the memory, and it can also read the information from the memory during the inference time. So it is just not it is not just memorize the execution steps. It learns to execute the algorithm steps. So there is a little example how the sketchpad works. There is model output, which means it is the context window. You can see there is read assignment with the special token, and it just say read something from the sketchpad. It reads and it continue with propagate some next steps. So the next thing which we are using is structure masking. We would like to compute loss only for the trainable token. We use our tokenizer, basically with non-English tokens, only use only the tokens from the CDCL trace. So we don't want to compute the loss for tokens like this or this. We would like to compute the loss for backtrack, unset, and so on. And we would like also mask the special tokens derived, like read, begin, and so on. So now I would like to talk about the data sets. We just synthetically generate 1 million of execution trace. And we just instrument the CDCL solver to capture our execution steps. So we have in distribution training data, and it is also for the validation and testing. And out of distribution, this is only for testing the generalization. And the difference between in distribution and out of distribution is just the number of variables. There is also the table with trace type. Because the execution trace is too long, we need to divide all the, not all, but we would like to divide the data to these steps. So we can predict the main loop, then we can predict the unit propagation, and then we can predict only the analysis. And from this information, we can compute the output. So now I'm going to talk about the model architecture. We use GPT Neo X with 12 layers, 16 attention heads. This is a very small model. It is about 9 million parameters, and it is basically 1,000 smaller than GPT-4. As I said, we use domain specific tokens, and we use this small model because we would like to iterate fast during our research. So the training time is about 2 hours. So now I would like to show you our results. We basically trained 3 separate models, 1 per task, and we tested them on 512 examples. Here you can see the results for the token accuracy, and here you can see the results for exact match accuracy, which means we can compute only the tokens or only the sentence. In a distribution, the result is quite good, but there is a little bit problem with out of distribution data. And this is because the clauses are very large. So basically, there is some information about our results. The main problem is only the out of distribution data. And that is all. So we showed we can train the reasoning step on very small large language models. It performs very well on in distribution data, and we show the Scratchpad enables the reasoning. There is also limitation, so there is accuracy drop between the in distribution and out of distribution data, and the longer trace provide more errors. So for the future work, we would like to focus on hybrid solution, which is the combination between the solvers and large language models. It is all. Thank you for your attention. Okay.
All right. So my question is, did you notice any like interesting behavior of the language model, something that would be unusual for the solving this kind of problems, something that you would, I don't know, consider innovative or weird? Like, was that something that you were not expecting when solving the formulas whenever they are satisfiable?
I have no idea.
So you didn't like dive into like actual step, and now this is weird, so this is strange step.
No, not exactly. I do this with my colleagues,
Okay.
and we prepare this, and everything works very straightforward.
All right.
But for now, we have some improvements, but we would like to continue after this conference. So I have no idea what
All right.
what is the next steps.
Okay. My second question is, you might have mentioned it, and I apologize if you did, but these three tasks, conflict, unit, preparation. So solving means whenever it's solvable or not. Conflict means if there is
the solve is basically the main loop.
Right. The conflict is what you've shown, and this unit propagation is.
Yes, unit propagation is basically the method from the CDCL solver, and that is this propagation, unit propagation. We check the clause for force assignment.
Okay, so these are three different categories of the things it does, and you measure on three. Okay. Then about the training, you have there was the slide with the training and masking. So what is the masking for? Because I see the masked over there, down there is like a read begin, read end. You said it's like the special tokens you are masking out?
Yeah, this is the special tokens, and we would like to perform the masking because the model can start trying to memorize the data. So for example, we don't want to train x1 is true. We just put it to the scratchpad, which is the storage, and we just train the types like backtrack or unit propagation and so on.
So it means that based on these special tokens, the network or the model could memorize the actual samples.
Couldn't, because we use the masking and we
Yeah, no, but if there would be no masking, the model could technically, if you wouldn't mask, just based on these tokens, it would be able to memorize.
Yeah, because you can basically train the x1 is true, x2 is false.
So it's in between the text. Okay, sorry, no, I misunderstood. Okay, so it's between those texts, the whole thing is gone. Okay. Then, so when you were talking about your data sets, this one. So these are quite high numbers, but then you said you are testing on a 500. Do I get it correctly that it's like a small subset of this whole data set?
Small subset?
Well, you said 500, and here I see like 1 million.
And this is because we use 500 for this, and for this. And this is the question. I don't know why they did.
But do I understand correctly that this means 200,000 samples, but you're gonna test only 500? So it's not like this is tokens and the other is like whole thing.
No. It is the trace. We are talking about the trace.
Okay, I do not know what trace is.
It is basically the file, and the file is, you can imagine like
the execution of algorithm?
Yeah, this
so this is the trace.
Yeah.
And this is also one sample?
Yeah.
So when you say I tested on 500, that means I tested on 500 traces. And the data that you showed, this 400,000, that is number of traces.
Yeah.
So you have tested out of 200,000, you chose 500 and tested on that. Okay. Sorry, I think it's pretty much my last. Right. One more question. Sorry.
Okay.
We are ending anyway. So my last question is, this in and out distribution differs in number of variables. and you said that or it was written the number of variables, the more variables, the longer it takes. And also, obviously, the accuracy dropped, or whatever that, yeah, accuracy. Do I understand correctly that it is probably because there is a more space for making a mistake in this execution of the...
Exactly. And
So
when you
could it
have,
be like related to hallucination, that you give
it is
more
not,
chance?
it is basically not hallucination in this way. The problem is you need very big context window for large format. And in this case, you also need a lot of conflict analysis.
So it could be related to the paper I saw.
Yes,
that
the problem is
first tokens are the most important,
it is long.
and the further you go in the context windows, the less important they appear to the model.
Yeah.
And so there is more prone for making the error.
Mhm.
Okay, so it's not really about the length of the trace or the number of steps,
It is,
but
it is also,
but it's more like you need to fit it into context window, and that is the issue.
Not exactly. It is also about the length of the formula, because you need for the long formula, you need to call a lot of conflict analysis, and the model can make a lot of mistakes.
And all of this goes back into the context window. So like appending, appending, appending.
For the context window, we use only the solve, unit propagation, and the conflict. We just divide the large execution step to these tasks.
And they go separately to model.
Yep.
So it's not appending bigger and bigger and bigger. But
No.
It's like a subtask. Do this,
Yeah, it is
result.
subtask.
Do this, result. Do this, result, and then
Exactly.
aggregate. All right. That's all my question. So thank you, David, once again. And with that being said, this is the end of the session. Thank you very much for the attending.